السلام عليكم ورحمة الله. إن شاء الله اليوم نكمل ما بدأناه من محاضرات الإحصاء، وكنا قد بدأنا بمفهومين مترابطين هما تحليل الانحدار وتحليل الارتباط. وكنا قد بينا سابقا بأن الارتباط يعبر عن علاقة بين متغيرات، وتناولنا الارتباط الخطي البسيط، العلاقة الخطية، وتكلمنا بعدها بالفرق بين الارتباط والانحدار عندما نتحول في هذه العلاقة إلى علاقة اتجاهية يكون فيها سبب ونتيجة. السبب سميناه متغير مستقل، والنتيجة أو الاستجابة سميناه المتغير التابع أو الاستجابة. فاليوم بقى لنا مفهوم من مفاهيم الارتباط الخطي البسيط الذي هو مرتبط بمعامل ارتباط الرتب لسبيرمان راح نتناول. فمحاضرتنا راح تكون منقسمة إلى بعض الأفكار بالتسلسل، ابتداء بمراجعة عن مفهوم الارتباط، ثم ننتقل إلى فهم وتفسير قيمة معامل الارتباط من خلال مقدار هذا المعامل. الأمر الآخر اللي راح نتناوله هو فهم قيمة معامل الارتباط من خلال الرسم. كذلك راح نتعرف متى نحتاج أن نستخدم معامل ارتباط الرتب لسبيرمان، ثم نتناول أصل مفهوم معامل ارتباط الرتب لسبيرمان. الأمر الآخر اللي راح نتناوله هي الصيغة الرياضية وتفسير مستوى أو قيمة معامل الارتباط من حيث قوته أو ضعفه أو انعدامه، سلبيا كان أم إيجابيا. وكذلك راح نتناول مثال نحلل فيه بيانات حقيقية. الأمر الآخر اللي راح نتناوله هو الميزات والعيوب الموجودة في معامل ارتباط الرتب لسبيرمان. وفي النهاية، في نهاية محاضرة اليوم راح نتناول شيء أشبه بالدليل لتحديد المقياس المناسب لحساب أو قياس العلاقة. يعني راح يكون عندنا جدول معين نبين منه نوع العلاقة التي يراد قياسها والأداة المناسبة لهذا القياس. وفي نهاية المحاضرة كما اعتدت دائما هنالك مراجعة، يعني راح نبتدأ باستطلاع لما سنتعلمه وفي النهاية سنراجعه. فالآن راح نبدأ إن شاء الله بمحاضرتنا للسمبل linear correlation، وبالأخص معامل ارتباط الرتب بسبيرمان rank correlation. فأول ما نبدأ راح يكون عندنا مفهوم الارتباط. يعني بداية هذه هي what we are going to learn by the end of this lecture: a review to general concept of correlation. Number 2, understanding how to interpret the value of the correlation coefficient through its amount. Number 3, understanding the value of the correlation coefficient through graphs. Number 4, when do we need to use Sperman rank correlation coefficient? 5, the origin and concept of Sperman rank correlation coefficient. Number 6, mathematical formula and interpretation of correlation scale. Number 7, real data analysis example. Number 8, merits and limitations of Sperman rank correlation coefficient, which we are going to call the advantage and disadvantage of Sperman rank correlation coefficient. And then we are going to have some kind of a guide to decide which measure of relation to use. And finally, we are going to review what we learned in this lecture. We start by the meaning and the origin of rank correlation, and we have here the a photo of Charles Sperman, the scientist who proposed this correlation coefficient. As you see, his name is Charles Edward Spearman, from 1863 to 17 September 1945. He was an English psychologist known for work in statistics as a pioneer of factor analysis and for Spearman's rank correlation coefficient. First of all, we have to review the meaning or the concept of correlation between two random variables x and y, which is what we can show as a measure of the degree of relation or of linear association between the two variables x and y. The population correlation coefficient is denoted by rho. This is a Latin symbol and can take any value from -1 to 1, which means no correlation coefficient is less than -1 or greater than 1. So, if rho is -1, this indicates a perfect negative linear relationship, or rho can be between -1 and 0, indicates a negative linear relationship, any value between -1 and less than 0. So any value means negative relation, and if rho is equal to 0, this means that no relationship between the two variables x and y. When rho is greater than 0 and less than 1, this indicates a positive linear relationship. When rho equal to 1 finally indicates a perfect positive linear relationship. So when rho is -1, we have a perfect negative linear relationship, and finally the last value or the maximum value that the correlation coefficient can take, if equal to 1, this indicates a perfect positive linear relationship. The absolute value of rho indicates the strength or exactness of the relationship. So here we have a graph as you see here. So this for example, to the left hand side, the upper graph in the corner, when rho equal to -1, we see here that there is some kind of straight line but going negatively, which means when x goes up, y goes down, which means as much as x is larger, as much as y is smaller, and in perfect manner, which mean the amount of increase in x can have the same amount of decrease in y, so that we see that we have some kind of line here, a negative line. If you look down, you see this one, rho equal to -0.8. This means that we have a negative relation but with correlation coefficient less than 1, as you see, -0.8. So we do not have a line like what we see above, but you see we have a negative correlation but less than greater than -1, which is -0.8. So when we have this negative correlation, as you see, and we have those points distributed negatively when x increase, y decrease. If you look to the second column, when we have this rho equal to 0, as you see here, we have rho equal to 0, then as you see, there is no relation at all, a linear relation and any other relation, because as you see, the points are distributed randomly. There is no pattern. We cannot see any pattern for the data, so that the rho is equal to 0. But if we look in the same column down to the second graph, we can see that we have also rho equal to 0, but if you look here, you can see some kind of curve here. So when rho equal to 0, this means that there is no linear correlation. But if we look to the graph, that's why the graphs are so important in many times. You see that there is some kind of curve. So this means that there may be a nonlinear correlation, but rho equal to 0 because there is no linear correlation. Now, if we look to the last column to the right, if we look above, we have here rho equal to 1. So when rho equal to 1, we have a perfect positive correlation coefficient or correlation in general. So we see a straight line as we see there to the left, but here the straight line is positive, which means when x goes up, y goes up as well in a perfect manner, which means the amount of increase in x can follow the same amount increase in y. So if we look down to the same column, the last column, we see here that rho equal to 0.8, which means less than 1. We see a positive correlation here, but not a perfect one, but it's clear that the correlation is positive when x increase, y increase as well. So these cases we can have when we analyze any data between two variables x and y. So now Sperman correlation coefficient is used if the variables examined. So this is some kind of a guide. If someone asks me, when can I use Spearman correlation coefficient? Because as we know before, we have a person, a correlation coefficient. So now we have a Spearman correlation coefficient. We can use it when we have ordinal or interval or rational level variables. So we have three cases. So the ratio level, if you see there, we don't meet the persons, which means the person correlation coefficient assumptions, such as normality of distribution, because one condition of applying person correlation coefficient is the normality. When we don't have normality, here we can use the Spearman correlation coefficient as we see here. So now if we go there, we see that the Sperman correlation coefficient or Spearman rho is named after Charles Sperman, as we see before. This is used to determine the strength of relationship between two variables of ordinal type. Use Greek letter rho. This is what we saw before. A non-parametric measure of statistical dependence between two variables. Please concentrate here. Non-parametric measure, which means a non-parametric measure of correlation. So we see here a non-parametric measure of statistical dependence between two variables. Now, if we have to look to the mathematical formula for this Spearman correlation coefficient, we see here that rho is equal to 1 minus 6 times summation d square over n times n square minus 1, where r is the rank correlation coefficient, and later on we are going to have some kind of example, and we will discuss this later to see how to find those ranks. So here, if we look there, we see down the r, which is the rank of correlation, summation di or d square, the sum of the square differences between the sets of ranks. We are going to see later on that the ranks of variables can be found by arranging the values of the variables and giving a rank, a smaller rank to the largest value and a largest rank to the smallest value, as we are going to see later. So if we look here, we see that n is the total number of observations. So now if we look to this row, 1 minus 6 times summation d square over n times n square minus 1. The d is the difference between ranks, n is the total number of observations, so this is the mathematical formula. So now if we look down here, when the rank, look here, when the rank equal to 1, rank number 1 should be given for the negative value, would be given for the highest value, sorry. The last rank, the largest rank, should be given for the lowest value. As I said before, when we are going to give ranks, we give the rank number equal to 1 to the highest value, and the we should given the largest value for the lowest value, which means when we have a small value, we are going to give a large rank. When we have a big value, we are going to give a small rank, as we are going to see in the numerical example. So now if we look here to this scale to see the interpretation of this rank correlation coefficient, as we say before, the correlation coefficient value is between -1 to +1. So if we look to this scale, we notice that the values, or the range of values, is between -1, as we see here, and 0 when there is no correlation, because you see perfect negative correlation when equal to -1, 0 when there is no correlation, and here +1 when we have a perfect positive correlation, as we discussed before. The plus sign indicates a positive correlation. The scores on one variable increase as the scores on the other variable increase. So we have here scores. We are going to transform to ranks. The positive value means the scores of the first variable x. When increase, this leads to increase in the scores of the other variable. So the negative sign indicates the inverse of this thing, which means when the scores on the variable 1, which means for example x, increase, the scores on the other variable will be decrease. So now if we can if we want to have some kind of scale to to answer the following question: what size or amount of correlation means when we have a different values, which means a value close to 0 positive, or close to 0 and negative, or close to 1 and positive, or close to -1 a negative value. As we see in this table, we have the first line here. We can see that when we have a value of rho, a plus minus 0.8 to plus minus 0.99, this means a high correlation. Then when we have a value of correlation coefficient plus minus 0.6 or 0.60 to plus minus 0.79, this means a moderately high correlation. Then when we have a small value of correlation, as you see, 0.40 to plus minus 0.59, this is also a moderate correlation. So here, as we see, we have a moderate correlation and then moderately high correlation. So what about the low correlation? As we see there here, we see plus minus 0.2 to plus minus 0.39. This means a low correlation, negative or positive. Finally, here we look plus minus 0.10 to plus minus 0.19. This is a negligible correlation, which in different way means a correlation is too low. It's some kind of no correlation, but there is a value, but this value is very small. For example, if we look here, 0.10 means from every change in variable 1, there is only a 10 change in variable 2 similar to that change, increase or decrease. As well as here, we have 0.19, which means from every increase or decrease in variable 1, there is only 19 decrease or increase or same decrease and increase in variable 2, and this means that there is 0.81 different change from in variable 1 compared to variable 2. That's why we said that this is a negligible correlation, which means nothing, is a very weak correlation. So now, if you want to interpret the correlation coefficient, the sign of the Spearman correlation indicates the direction of association. As we say before, when we have a positive value of correlation, means when the scores of first variable increase, there is an increase in the second variable. Also in the same way, when the sign of the correlation is negative, this means that when the scores of the first variable increase, then the scores of the second variable decrease. So that here, if we look, the sign of the Sperman correlation coefficient indicates the direction of association between x, the independent variable, and y, the dependent variable. Here, I want you to notice something. Here, when we said the independent variable and y, the dependent variable, in the correlation, we don't have independent and dependent. We have two variables, and we measure the linear correlation coefficient between them. When we turn to regression, then the meaning of independent and dependent have a specific meaning. There is an independent variable x and dependent variable y. The x is explanatory variable, the y is the response or the explained variable. Then we have that cause and effect. But here in the correlation, when we say x independent and y dependent, we just find the amount or the strength of the correlation between the change in variable 1 to the change in variable 2. Increase to increase means positive correlation. Increase in the first one and decrease in the second one, a negative correlation. Now, if we look here, if y tends to increase when x increase, means that x and y increase together, the Spearman correlation coefficient is positive. Sure, when we have both the two variables, both increase, then as we see, increase in x and y also increase, this means that the correlation coefficient will be positive. If y tends to decrease when x increase, then this means that there is an opposite change between x and y decrease and x increase, then the Spearman correlation coefficient will be negative because the first variable increase and the second one decrease. So now if you want to have an example, we have a table show the rating of a group of 10 supervisors who have been evaluated independently for leadership on a scale of 1 to 10 by the production manager and by the workers whom they supervise. Calculate rho to determine if there is a correlation between the two variables. So if we look here, we have those supervisors. As we see, we have 10 supervisors, A, B, C, D to J. The workers evaluation X, we have 4, 2, 2, 1, 7, 9, 3, 5, 2, 7, and also the workers evaluation Y is 3, 4, up to 5, 3, as we see here. Then, if you want to find the Sperman correlation coefficient, we see here that the supervisor A have x equal to 4. If you look to the rank of x, we see here that the rank is 5. If we look back here to the values of x and want to arrange them from the smallest to the largest, we see that here we have the number 1, also we have number 2, and also number 2 again, and there's another number 2 down there here. Also we have number 3, we put 3 here. Then we have number 4 up there, and we have 5 here, we put 5. Then we have 7 twice, so here we have 7, and also 7 again. We have here, as you see, 7 here and 7 here. Also we have 9 here, so we put 9. So if we look now, we see that there is 1, 2, 2, 2, 3, 4, 5, 7, 7, 9. If we look here, we found that the value 4 for x, this one, got a rank of 5. If we look here, we find that here that we got here the 1, we as you see here, the 9 will be taken a value of 1. As I said before, we say that for the largest value we give a small rank, and for the smallest value we give a large rank. So we are going to start from the largest to the lowest, as you see here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here, when we look to this one, the rank 5 for number 4, if we look here, 1, 2, 3, 4, 5. So if you see here that for the value 4 in x, the rank will be 5. That's why we put 5 here. So let's choose another one. We look here. We found here that for the value of x equal to 7, the amount of rank is 2.5, and the question is, how do we get this 2.5? So now, if we look to the value 7 and 7 here, look, we have 7 twice. If we look to the ranks of these two values, we found here 2 and 3. So 2 plus 3 over 2 is equal to 2.5. That's why we got here a 2.5. So here we got 2.5 as a rank of the value 7. So let's choose another one as an example. If we look here to the value here 2, look here to the number 2. If we look to 2, we found that the rank is 8, and the question is, how do we get a rank 8 for a value equal to 2? So if we look up there, we found here for the values equal to 2, we got a rank equal to 8, as we see here. And if we look back, 1, 2, so if we look back here, for number 2 we have 8. So when we arrange the values, let's arrange them from the largest to the lowest. The largest is 9, then 7, 7, then 7 twice, yes, and there is no 6, there is 5, and 4 as well, and there is 3, 3 once, yes, and there is 2, 3 times, 2 and 2 and 2, and there is 1. If you want to see how do we get a rank of 8 for a value of 2, let's look to number 2. Here, for the largest value, we give a smallest rank. So for number 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for number 2, we see here that we have, for number 2 here, we have 7 plus 8 plus 9 over 3. 7 plus 8 is 15, plus 9 is 24, 24 here, over 3. 24 over 3 equal to 8. That's why we got an value of a rank equal to 8 for a value of 2. And that's how we calculate ranks for these variables. The same thing done for the variable y. For variable y, also we are going to arrange the values from the largest to the lowest. So if you want to try to do this, we see that the y, the largest value of y is 8. We have 8, the value 8 twice, 8, this one, and also this one. Then we have 8 again, then we have 7 once, we have 6 as well, once as well, 6, and then 5 twice. This is a 1, 5, and the other one here, so 5 and 5. Then we have 4 up there, So 4 here, the second value, we have 4, and then we have 3 twice the first value here, and the last value is 3, so we have 3 and 3 again. Number 2 we don't have, we have 1, so here if we count 1 2 3 4 5 6 7 8 9 10. Okay, now if we look to the ranks of y, for example, if we look here for the value 7 in y, the rank is 3. So let's see, how do we get a rank of 3 for a value equal to 7? Look here. Now, after we arrange the value from the largest to the lowest, and as we say before, we give the largest rank to the smallest value and the smallest one to the largest value. So let's try here to do that. So here, let's erase this first. Okay, and then this one, and let's try to write the ranks. Now for the largest value, we give the smallest one. 1 2 3 4 5 6 7 8 9 10. Okay, now if we want to check the ranks, for example, now let's see, for the value equal to 5, the rank is 5.5, and the question is how do we get a value of 5? Sorry, here we have 5 twice. Yes, here 5 twice here. As you see, we have number 5 twice, and if we look for these two 5s, there is a rank 5 and 6. So 5 plus 6 over 2 equal to 5.5. That's why we got here a rank of 5.5. Let's choose another one. Now, for example, for the value equal to 8, let's try 8. 8 here, the rank of y for a value of 8 is 1.5. If we look here, we found that we have two 8s, and the ranks of them are 1 and 2. As we do before, when we have a serial ranks, we sum up all those ranks and divide by the number of ranks. So we have here two ranks for number 8. So 1 plus 2, let's write it here, 1 plus 2 over 2 equal to 1.5. That's why the rank of 8 here is, as you see here, 1 plus 2, the value of 8 is 1.5. That's what we just found. Okay, then if we look here, we found that there is what we call the D. If you remember, we have 6 summation D square over n times n square minus 1 minus. If we go back, the formula, if you remember, we see here there is 1 minus 6 times summation D square over n times n square minus 1. So here, if we go to find those values for our real data example, look there. There is D, and as you see, the first D is minus 3.5. How do we get this? As you see here, 5 minus 8.5 is minus 3.5. Let's choose another one. For example, this one. How do we get it? 2.5 minus 3 is minus 0.5. Let's see here. How do we get number 2 for G, for this supervisor? 6 minus 4 is, so D is the difference between the rank of X and the rank of Y. That's how we got some negative and positive value. For example, this is a positive value, 2.5. So it's 8 minus 5.5, which is 2.5. Then the last column, as you see here, is D square, which is what we need. As you remember, the row is 1 minus 6 summation D square over n times n square minus 1. So we need all those amounts to get the row value. So now here we got the D square. So let's see here, 12.25. How do we get it? By squaring the first D value. 3.5 negative times negative 3.5. As you know, negative times negative is positive. 3.5 times 3.5 is 12.25. Let's choose another one. Let's see here. How do we get this? By squaring this 2. 2 square is 4. How do we get 6.25? By finding the square of 2.5 and so on. So now all the things we need to get the value of the correlation coefficient now is ready to use. So if you want to find it, as you see, we just write rho equal to 1 minus 6 times summation D square, as you see down there, is 72 times 72.5 over n is 10 times 10 square, which is 100 minus 1. So here, if you want to see, as you see here, rho times 6 summation D square times over n times n square minus 1. So 6 times 72.5, as we see here, is 435. Here 10 times 10 squared, so 10 times 100 minus 1, which means 10 times 99, which means here, as you look here to the right hand side up in the corner, 1990. And then rho is 1 minus 0.44. How do we get this? By dividing 435 over 990. Then 1 minus 0.44 is 0.56, which means there is a positive correlation coefficient between X and Y. So there is a moderate positive correlation. As you see, the value is 0.56. As we mentioned before in the table, this is a moderate positive correlation between evaluations of the personnel, managers, and the workers, as we saw in the data given in the example. Now, the question here is, how do we know the advantage, which we call in the second slide as the merits, the advantage of Spearman rank correlation? If someone asks me, when do you need to use this Spearman rank correlation? So the first one, as we see here, this method is simpler to understand. As you saw, when we solved the example and we looked to the mathematical formula, we found that the calculation is too simple. We just find the ranks and the difference between ranks, then we square them and then we use the formula. So this method is simpler to understand and easier to apply compared to Person correlation method. So this is an easier to calculate than Person correlation coefficient. This method is useful when we can give the ranks and not the actual data. So if you look here, this is an important thing. If we look here, a qualitative term. So sometimes we want to have a correlation coefficient between a qualitative terms, not a quantitative one, not a real measures, not a real values, but a qualitative terms. So we transform those terms into ranks. Then we can find the Spearman correlation coefficient. Also, this method is to use where the initial data is in the form of ranks. So if you have already a ranks, then the Spearman correlation coefficient is very useful to use when you have already a ranks. Also, here, if you look, it is a non-parametric, so you don't have to have a normal distribution. If you remember when we discussed the Person correlation coefficient, we need that the data is distributed as normal distribution, but here we don't need to have a normal distribution. Also here, if you look to the last one, you notice that there is some kind of a mention to the effect of outliers. If you look here down, you found that it's less affected by outliers, and the question here, how we can call that the Spearman correlation coefficient is not affected by outliers. If you remember, the calculation of Person correlation is using the actual values, the data we have. But here we don't have to use the real data, but we are using, as you saw, the ranks of those data, which means when we have an outlier, a very large value or a very small value, then we are going to get the rank D for that value, not the actual value. So it will be not affected. But if we are calculating a Person correlation coefficient, the Person correlation coefficient use the actual values, the real value, so it will be affected by outlier, which means here, if we have outliers in the data and we need to find the correlation coefficient, using a Spearman correlation coefficient is better than a Person correlation coefficient when we have an outliers in the data. So now, the opposite properties, which are the disadvantage of a Spearman rank correlation. So here, when we want to talk about the disadvantage, if we look to the first one here, we see that it cannot be used for finding out correlation in a grouped frequency distribution, but we can use the Person correlation coefficient for the frequency distribution, and we cannot use the Spearman correlation coefficient. This method should be applied when n exceeds 30. So here, when n exceeds 30, we can use, which means when we don't have this range of value, we cannot use the Spearman rank correlation. So those are the disadvantages of Spearman rank correlation. As we discuss in the second slide, if you remember, we talk about having some kind of guide to find the relation of between data, and that's what we call a guide to decide which measure of relation to use. And if you look here, this is some kind of guide you can use when you want to find a relation. Let's look to the first line here, this one. When we have a nominal data or ordinal data to find the correlation or the relation between the variables. We look here, variables involved in the association being tested, and column number 2 is the test suitable for that case, and then an example. If you look in the first line, we notice that when we have a nominal or ordinal variable, the suitable test is chi-square. For example, is there an association between shift worked and marital status among nurses at my hospital? Then the chi-square will be suitable for this type of data. Let's have a look to line number 2. When the variable involved in the association being tested is ordinal and ordinal, so this means that when both x and y are ordinal, the available test here is Spearman correlation, which means when we have nominal or ordinal, we use chi-square. Now, when we have the both variables are ordinal, the Sperman correlation will be suitable. For example, let's have a look to the second line in the last column here. Is there an association between heart rate, HR, and pain in hospitalized children? HR measures as beats per minute, pain measure as mild by moderate by severe. So this is an example of two ordinal data. So we use Spearman correlation. If we look to the interval ordinal and interval ratio, if not so, here we can have ordinal and ordinal and interval ratio if not normally distributed. Both those two cases we can use Spearman correlation. So now, when we have nominal or ordinal data variables, we use chi-square. When we have both variables are ordinal, or one of them is ordinal and the other one is interval or ratio and not normally distributed, we use a Spearman correlation. Finally, when we have the variables are interval and ratio, we use Pearson correlation. So here, if you look to the second line, you see ordinal and interval but not normally distributed. But here in the last line, interval and ratio as well as the second line, but here normally distributed. For example, is there an association between heart rate and the blood pressure among men attending an alcoholic anonymous meeting? So here the Pearson correlation is more suitable than Spearman correlation. The Spearman we use when we have interval ratio for non-normal distribution, but when we have interval ratio for normal distribution, we use Pearson correlation. So this table is some kind of guide for you to use when you want to find a relation. Finally, if you look down here, these tests simply look for associations or relationships, not differences between groups. For example, in a sample of nurses working extended shifts, a relationship was found between hours worked and the number of medication errors. So this is an example of a case we need to find a correlation. So now, if we want to have a review for the lecture for today, we see that we discuss the population correlation denoted by rho. can take any value from -1 to 1, and as you remember, we call the negative one a correlation coefficient equal to -1 as the perfect negative correlation, and positive one as perfect positive correlation. The Sperman correlation coefficient is used if the variables examined are ordinal, interval, or ratio levels. The formula, as you remember, is rho equal to 1 minus 6 times summation d square times over n times n square minus 1. R is the rank correlation coefficient, and summation d square is the sum of the square differences between the sets of rank. N is the total number of observation. Then the plus sign indicates a positive correlation, means that the scores on one variable increase as the scores on the other variable increase as well. The negative sign indicates a negative correlation. The scores on one variable increase, then the scores of the other variable decrease, which means an opposite change. When the first one increase and the other one decrease, or the first one decrease and the other one decrease, the correlation will be positive. When we have opposite one, we have a negative correlation, which means that when the first variable increase and the second decrease, or the first decrease and the second increase, we have a negative sign. The coming lecture will be used to discuss the usage of SPSS data, and we are going to use Arabic language. As you see, موضوع المحاضرة القادمة الارتباط الخطي البسيط والانحدار الخطي البسيط مع التطبيق على برنامج SPSS. وشكرا جزيلا لكم، وإن شاء الله الجزء الثاني من المحاضرة هو سيكون تطبيق لبرنامج SPSS في موضوعي الارتباط والانحدار. راح نتناول موضوع الانحدار البسيط والمتعدد، والارتباط ارتباط بيرسون، وارتباط سبيرمان للرتب. أيضا راح نتناوله بكافة خطواته المتسلسلة ببرنامج SPSS. فإن شاء الله المحاضرة أو الجزء الثاني من هذه المحاضرة اللي هو التطبيق على البرنامج راح يعني نتناوله في الجزء الثاني اللي يرسل لكم إن شاء الله يوم غد. شكرا.